Okay, so we'll begin, right. So, in the last class we introduced forces and interactions in colloidal system, and the way we did that was by looking at Brownian motion, right. This video did not play the other day, so I am just going to play this. So, that is these are fluorescently labeled particles which appear bright, they more like look spherical, right. They are spherical particles which are being continuously bombarded by the solid molecules, and if you look carefully they are not really moving in any particular direction, right. They are just about there in some location and they are jiggling around, right. And that is what is called as Brownian motion. And what we did was we used this as an example, and then I told a little bit about how carefully these experiments were designed, right, to estimate the Avogadro number, right. And then in doing so we just said that there should be absence of certain forces on the system, and there should be some absence of interaction between the particles and the particles on the wall, right, in which the experiments are done. So therefore, that is how we kind of introduce you to the concept of interaction of force on the particles and then interaction between the colloidal systems. In terms of force, we talked about the force of gravity, right, Brownian force. Okay. We talked about hydrodynamic force. Okay. It was also called as drag force as well in this case. Plus we also mentioned something about osmotic pressure force. Okay. Okay. And having an idea about what is the typical magnitude of each of these forces on the particles or the magnitude of forces in a colloidal system would help you to design good experiments. Okay. And similarly we said that whenever you have many more particles, okay, if the particles are very far apart, then you do not have to worry about interactions, but typically when you work with a dispersion which contains large number of particles, when the particles are sufficiently close, then we should talk about what are called as interparticle interactions. Okay. That is not on the individual particles, but if you have particles in the immediate vicinity, okay, then you talk about the interaction between the colloidal particles. When I say vicinity, again it is relative, right, depending upon the kind of forces that you are dealing with. Okay. For example, if you talk about van der Waals forces, which will expand further, typically this van der Waals force of interactions is operative when the distance between the particles is about 10 nanometer or less. Okay. That means if you have any distance which is larger than this, you do not have to worry about van der Waals force of interaction. Okay. So we talked about van der Waals force of interaction, we talked about surface forces, right, and surface forces we said that the surface forces can come about if you have particles that could have charge, and the particle which could have some adsorbed ions, adsorbed polyelectrolytes, surfactants, nanoparticles, right. So it could be anything on the surface of the particle, and that could lead to some interactive forces. Then we also mentioned about something called as a depletion interactions. Okay. And we mentioned that such interactions would only come into picture whenever you have a colloidal particles in a fluid, and to that you add a polymer or any particles such that the size of the polymer or the particle that you have added is much smaller than the particles which make up the dispersion. Okay. So again we will discuss this at length. Plus we also mentioned the final type of interaction which are what are called as hydrodynamic interactions. Okay. And we said that such interactions would only come into picture whenever there is flow, right. That is what that is where we had stopped. Okay. So what we are going to do today is to look at the analysis of the Brownian motion a little bit more than what you have done so far, okay. And then we look at its application. Okay. That is what we are going to do today. Okay. More specifically, I am going to look at these three things: use of Brownian motion for measurement of what is called the particle diffusivity, okay, and extend that to measuring the size of the particle. And then I will also hopefully give you some hint as to how can one use this Brownian motion for looking at what is called as a sol gel transition. Okay. That is what we will try and do in this lecture. Okay. So, this is again I have already showed this, right, 3 tracks of this is track 1, track 2, track 3 of 3 particles that are exhibiting Brownian motion. And so, you have these dots, right. These dots correspond to particle position, okay, at some time. Okay. So, in this case I could say that this could be particle position at time t is equal to 0. Okay. Next, whatever dot that you see here, it is at time t is equal to 30 seconds. Okay. And the next one again from here it has come somewhere here, right. That is your so basically the way it is done is you take a video of a particle exhibiting Brownian motion, okay, and I locate the particle position, right. This is a 2D space, right, x and y, okay. I can find the coordinates of the particle, I get that, and that is what I have plotted here, okay. And I take another frame 30 seconds apart and I look at what is the particle position in that image and I put that here, okay. I go on doing that until I have done sufficient averaging. In this case what you see is is, for example, if you look at this, I think there are about 30 segments. What do you mean by segment is the distance between particles in 2 consecutive frames, that is a segment. Okay. So, there are 30 segments and each segment is 30 seconds apart. Okay. I mean, if you look at, right, if I look at the distance between the 2 particles, it has travelled so much distance in 30 seconds. Okay. Now, so if I have a figure like this, okay, from this let us say that I want to calculate what is called as a mean square displacement. Okay. I can do that by an image like this. Okay. So, what information that I knew is I should know that what is the scale of one division, right, because this is a graph, okay, and this one division, that is the distance going from maybe like say this to this, right, that distance, okay, that is 0.003125 centimeter. I know that distance. Okay. If you want to do it manually, what I can do is I can print it on a sheet of paper and I can take a scale, okay, and I can find out what is the distance between this and this, right. In if you are going to use a scale which has centimeters, I am going to say it as some say x centimeter, okay, and I can again similarly I can get what is this distance in terms of centimeter, let us say y centimeter. Okay. If I know the scale and what is the actual distance, I can actually get what is the actual distance that the particle has moved for every 30 seconds, right. I can do that, right. So, that data is basically plotted here. Okay. So, this is a segment number, okay, starting from 1 all the way up to 30 here, okay. And in the first segment the distance that is measured, okay, in millimeter is about 38, okay, and the last one is 32. Okay. Let us go back and look at these, right. The first one was here, right, that is your first, and the last one is here, right. Okay. The distance look comparable, right. One is one is 38, other one is 32, looks like they start from here, that is your first segment, okay, and then go on tracing it and come all the way there, right. So, that is the distance that the particle has moved, okay, in every 30-second time interval. Okay. Now, of course, you can use a scale and all of that, your scaling factor, all that, and you can get what is the actual distance that the particle travels in a given 30-second interval. Now I have the actual length the particle has travelled. I can take the square of that, okay, the square of the distance the particle has moved, okay, in the first segment, second segment, I can do all of that for all the segments, okay. And then, so this is basically your, now if I add them up all, and if I divide the number that you get by 30, that is what will give you what is the mean square displacement. Okay. Typically, it is given by x bar square. Okay. That is your mean square displacement. Okay. So, it turns out that if I add all these numbers up, okay, here what you get is something like this. It is 6634.8 into 10 power minus 8 centimeter square. Okay. And if I want to convert that into meter square, so that is going to be 10 power minus 4, right, meter square, right, and that divided by 30, okay, will give you a number which is something like 2.2116 into 10 power minus 10, okay, because you have 8 here, that becomes 12, right, and you have a, this is 1000, right. So, it becomes something like minus 10 meter square, okay, that is the x bar square, right. That now you have, so I said that every segment is it is at a 30-second time interval, right, and therefore, I can actually calculate what is the total time, right. The total time is going to be, I have 30 segments, okay, right, multiplied by 30, right, that is going to be your 900, okay, therefore, divided by 900 second, okay, that is going to be my x bar square divided by t. Okay. Now, we kind of introduced this equation that was derived by Einstein, right. So, where the mean square displacement, okay, is equal to 2 times d times capital D times t, where d corresponds to the dimension, right. So, if you are doing experiments in 1 dimension, d is going to be 1. If you are doing experiments in 2 dimension, d is going to be 2, right. Therefore, if I put all these numbers, okay, it turns out, so now because this is a trajectory in 2 dimensions, okay, therefore, whatever x bar that I have calculated, right, this is for 2 dimension. Okay. If I want to get what is diffusivity, what I need is delta x square of t, that is average, divided by 4 times t, right, because I am doing experiments in 2 dimensions. Therefore, your d is going to be whatever the number that you got here, that is 2.2116 into 10 power minus 8 divided by 4 into 900, right. Can you get this number for me if you have a calculator? Let us do that. It is 2.2116 divided by 4 and then divided by 900. Okay. That comes out to be something like 6.1 into 10 power minus 12, yeah, that is going to be in meter square per second, right. Now, so from these experiments, what you can do is you can actually get what is the diffusivity of the particles, right. Now, you can ask a question as to what is the, why do we need diffusivity? right. It turns out that I can use these diffusivity measurements for calculating what is the. So, in these experiments, so Perrin did experiments with particles whose size was known, okay. 0.52 micrometer was the size of the particle, right. Now, if you do not know this size, I can actually use these mean square displacement calculations, okay, from which I can get diffusivity to estimate what is the size of the particle. Okay. The way it is done is by using what is called as Stokes-Einstein relation. Okay. So, again, what we will do is what we are trying to do is we want to relate the Brownian motion that the particles exhibit to the diffusivity of the particles. Okay. Now, whenever you have a particle moving in a fluid, we say that there is going to be a drag force, right. That is the force that is exerted in the direction of flow, right. So, the drag force is exerted in the direction opposite to the flow of fluid, right. Okay. So, if the particle is moving like this, okay, and its movement is going to be hindered by the fluid, right, and it is going to experience a force in the direction opposite to its movement, right. So, again you would have learned this concept of drag coefficient in fluid particle mechanics or in your mechanical operation course, where the drag coefficient goes as what is called as Fd by Ap. This Fd is what is called a projected area that the fluid of the particle, right. If I have a like say if you have a stationary column of liquid, and if the particle is falling like this, if I see from the top, what I see is this circle, right. That is your projected area, right. And of course, if it was to fall like this, okay, then I am going to see if it is going to be a cylinder, I am going to see a rectangle, right. So, that is your projected area. So, that is Ap is the projected area, and Fd is the drag force, and u naught is the velocity with which the particle is moving, okay, and rho is a density of the fluid. Okay. Now, okay. So, because we are working with colloidal particles, okay, it turns out that because of the fact that the particles that we are dealing with are very, very small, right, of the order of 10 power minus 9 meter to 10 power minus x meter, it turns out that the Reynolds number that you calculate for any problem that involves colloidal particles is going to be very, very small. Okay. That means Reynolds number, which is the ratio of inertial forces to viscous forces, is going to be always small. Okay. In such cases, your CD goes as 24 divided by Reynolds number. Okay. Now, I can substitute for Reynolds number, that is going to be mu divided by dp u naught into rho, okay, and if I do some simplification, because I know that if CD is 24 divided by Reynolds number, I know that. Now, because your CD is again Fd divided by Ap divided by rho u square by 2, right, and Ap, the projected area, is going to be the area of the circle, right. Okay, that is going to be pi dp square. If I substitute for all of that, you get Ft as 3 times pi mu u into dp. This is again the well known Stokes drag, right. Okay. Essentially, you end up with the expression for drag for a spherical particle moving in a fluid, right. Again, you can do this by again starting with Navier-Stokes equation. I can start with the general equation, I can do appropriate modifications, and I can also obtain a similar expression, but this is one of the simpler ways of doing it. So, all that we have done is we got an expression for the drag force that is experienced by the particle, right. Now, because the particles are constantly moving in the fluid, the net velocity u naught, okay, with which the particles are moving is the average distance the particle moves, okay, in a given time interval, right, that your u naught is x bar divided by t. But now, whenever a particle is moving, okay, it has to get some energy, right, okay, or okay, so the work that is done, okay, by the moving particle is f d multiplied by x bar, that is force times the distance, okay, the average distance that it travels, okay, that is your the work that has to be done, you know, in moving the particle, right. Now, that energy, where does it come? It comes from the thermal energy, right. Therefore, the equating the thermal energy to the work that is required, you know, for moving the particle, okay, what I can do is I can equate them, okay, and because I know what is F d, I can substitute for F d from the Stokes drag, right, and this I mentioned that you have u here, right, u naught, okay, is x bar divided by 2, okay, and you have an x bar here, therefore, it becomes x bar square divided by t, okay, and because you have dp here, okay, and dp is 2 times r, right, therefore, this becomes 6 here, therefore, kBt is equal to 6 pi mu r x bar square divided by t, okay. Yeah.
Here, like, what is the cause for Brownian motion?
The cause for Brownian motion is the constant bombardment of the fluid molecules with the particle.
Okay. So, but we are calculating that the thermal energy will account for the drag.
Yeah, that is because see, if you take any container, right, say that, you know, I have water, right, and say that this water is maintained at a temperature T, okay. Now, so the energy that every molecule of water in this container will have is kBt.
Yes, the total internal energy is given like that.
Yeah,
So,
every molecule will have this energy.
yes, yes.
Correct. Now, that is what is being used for the mobility of the particle.
Yes, yes. So, we are assuming that all particles will move with a certain velocity.
No, we are saying that the molecules of water will have this energy, and this energy is being used for moving the particle.
But they have constant velocity.
Which will have constant velocity?
The particles.
Yeah, the particle will have an you know, some average velocity. See, if you go back here, right? Okay, let me put it this way. I mean, if you look at the length that we have got, right? Let's look at these numbers, right? The length of the every segment is what is calculated here, right? You look at the length here. So, you have 152.1 10 power minus 8 centimeter square, but you have numbers which are as low as 2.6 10 power minus 18. Okay, I mean, if you want to calculate, okay, velocity for every segment, it will vary in a certain range, right? But if you watch them for sufficiently long time, if you calculate the velocity, it will have I mean, if you go back when we did this force calculation, right, on different, okay, we said that a micrometer particle will typically move with 1 micrometer per second velocity, okay. Numbers like that are kind of obtained from experiments like this, okay. Yeah, so on an average, particles in a fluid which is maintained at a particular temperature will move with a velocity which is typically, again, depends on the size of the particle, right. If you have a 10 power minus 9 meter size particle, nanometer size particle, of course, it is going to move with a much larger velocity, compared to 10 power some particle which is a 10 power minus 6 meter size, right. Yeah. Now, this x bar square by T, that is what is the diffusivity of the particle. Okay. Therefore, you have an expression which relates the diffusivity of the particle to the thermal energy and the viscosity of the fluid in which the particles are dispersed or the particles are moving, right. R is the size of the particle. Therefore, if I have done an experiment where I have studied the Brownian motion, if I am able to calculate what is the diffusivity, if I know what is the viscosity of the fluid in which the particles are dispersed, I can actually use this expression and measure what is the size of the particle. Okay. Therefore, in essence I could use some technique like microscopy, wherein I have measured Brownian motion and I can back calculate what is the size of the particle if you do not know what is the size. Okay. So, you can think about this as a one nice application of Brownian motion, where people exploit this particular phenomena and then estimate the size of the particle, right. Any questions? No? Okay. So, we will okay, now you can go back and take a look at, so because we have measured diffusivity, right, from the earlier track that we looked up, right, and if you take water, say 0.001 Pascal second, right, that is the viscosity, and put in appropriate values for kBT 1.38 into 10 power minus 23, and temperature, I think what is taken in the in this reference is 290 Kelvin. If you put in all of that, you can back calculate R, and the value that you should get should be very close to 0.52 10 power minus 6 meter. Okay. You can try and do that and see how it works out. Okay.